Hello students, in the last class we have seen about the transistor AC equivalent circuit and the graphical analysis. In this class we are going to discuss about the small signal hybrid pi equivalent circuit and hybrid pi equivalent circuit including early effect, and also we are going to discuss about the expanded hybrid pi equivalent circuit. First of all, what is meant by this small signal? The small signal in the sense the signals which are in small in magnitude, which mean low amplitude signals, and also these signals varies with the time. It means that they are low amplitude AC signals. Okay, those are called small signals. So when we apply that small signals to our amplifier circuit like a transistor amplifier circuit, then what is the behavior of the transistor, like what is the gain of that amplifier and what is the input impedance and what is the output impedance that we need to get. Okay, but the VI characteristics of an active device such as BJT are non-linear, so it is very difficult to get the analysis of non-linear devices. Okay, so the analysis of a non-linear devices is complex. In order to simplify the analysis, we are going for the equivalent circuits. Okay, to simplify the analysis of a BJT, its operation is restricted to the linear VI characteristics around the Q point, that is in the active region. So which means that we are restricting the operation of the active device in the active region itself. Okay, so there we can get somewhat linear operating region. Okay, at that place only we are going to apply the analysis of this one. Okay, so this approximation is possible only with the small input signals. This entire thing is approximation analysis that is possible only with the small input signals. In the small signal analysis, we are going to replace the transistor with some equivalent circuit. Okay, suppose if you take a circuit that contains the BJT, okay, while applying KVL or KCL to that circuit, we don't know which component is at the input side and which component is at the output side in the BJT. Okay, the BJT itself a component and we don't know the behavior of the BJT, so that we are going to replace the BJT circuit with some equivalent circuit. That equivalent circuit will contain some resistance or some other equivalent component for the BJT response, and then we are going to apply KVL and KCL to that equivalent circuit in order to get the analysis of that transistor amplifier. And these models are called as small signal equivalent circuit models. Okay, so replacing the BJTs with some equivalent circuits is called as small signal equivalent circuits. Okay, so there are three models that are commonly used in a small signal analysis of a transistor network. These three models are RE model, hybrid pi model, and hybrid equivalent model, which is also called as H parameter model. Okay, in these three models, mainly we are going to use the H parameter model and hybrid pi model, and RE model is the simplest model. In our prescribed book, they have used hybrid pi equivalent model. In order to get the equivalent circuit of the BJT, we are assuming the transistor or the BJT as a two-port network. All the transistor amplifiers are two-port networks having two voltages and two currents. Okay, so all transistor amplifiers we can assume which are two-port network that contains the two voltages and two currents. Out of the four variables, we are going to consider the two are independent variables and the remaining two are dependent variables. Okay, this is the block diagram of the two-port network. Here I1 is the input current and I2 is the output current, and V1 is the input voltage and V2 is the output voltage. Okay, suppose if you assume the amplifier is a BJT type of amplifier, then we know that a BJT is a current controlled device. Therefore, the input current and output voltage we can take as independent variables. Okay, and the remaining input voltage, output current are dependent variables. So like that we will assume, and then we can able to do analysis for the BJTs. Here the dependent variables can be expressed in terms of the independent variables. Here we assumed the input voltage and output currents are the dependent variables, and input current and output voltages are independent variables. Therefore, we can write the dependent variables are the functions of the independent variables, like V1 is equal to a function of independent variables I1 input current and output voltage, and I2 current, that is a independent one, that is also a function of the independent variables input current and output voltage. Like that we can represent the independent variables and dependent variables in the small signal equivalent circuits. These expressions can lead to the different two-port network parameters like Z parameters and Y parameters, which are called as admittance parameters, and H parameters, which are called as hybrid parameters. Okay, so by using these equations we can able to get these three types of parameters, out of which we are going to use the H parameters mostly. And assuming that transistor as a two-port network here, and the graph between the input voltage VBE and the input current IB, therefore this graph is called as input characteristics graph, so which was drawn between the input voltage to the input current. What we are going to do is we are going to apply some VBE voltage between the base to emitter of the transistor. After application of some VBE voltage, we can get some current which was developed in the base circuit. That is called as a base current, that is superimposed on the Q point values here. This IB was superimposed on the Q point base current IBQ, where IBQ is a Q point base current, that is a DC base current value, and also this VBE voltage applied base to emitter voltage was superimposed on the DC biasing voltage VBEQ. The slope of the Q point is constant and which has the units of the conductance. So here the Q point slope is given by 1 by R pi, where R pi is the resistance and 1 by R pi is called as the conductance, which is the slope of the Q point. Therefore, the inverse of conductance can be treated as a small signal resistance R pi. Okay, so here R pi is the small signal resistance that is at the input side of our transistor. Therefore, this resistance will be available between the base to emitter of our transistor, which is called as R pi. Okay, therefore we can say the VBE voltage, when we apply KVL in this loop, we can get the VBE is equal to, according to Ohm's law, V is equal to I into R. Therefore, VBE is equal to the current in this loop is IB into the resistance in this loop R pi. VBE is equal to IB into R pi, where here all are AC quantities which are varying with the time. Therefore, all notations are represented with the small letters, and we can express 1 by R pi is nothing but the slope of the Q point, that is nothing but the conductance, that is equal to dou IB by dou VBE at Q point. Okay, so which can be expressed like I by V, input current divided by input voltage. Okay, so here dou IB by dou VBE is a change in the base current to the change in the base to emitter voltage. So here at Q point, in the sense we are assuming those values are the pure DC values. Okay, we know that the IB which is the base current, that is equal to IS divided by beta into exponential of VBE by VT. In the last derivation we have seen this is the value of IB. Okay, so when we substitute that value in the place of IB after the differentiation with respect to the VBE, we can get the 1 by VT into IS by beta exponential of VBE by VT, because IS by beta is a constant and exponential of AX, which is A into exponential of AX. Okay, so like that, this is a 1 by VT will come outside, okay, into Is by beta into exponential of VBE by VT at Q point. When we apply the Q point values here, the VBE will becomes as a DC value and VT is also a DC value, so that this entire term will be equal to the DC component. That DC component is nothing but the base DC component IBQ, the base current IBQ. Therefore, this entire term can be represented as IBQ and which was divided by the VT, volt equivalent temperature. Therefore, 1 by R pi, which is equal to IBQ by VT. Here we have derived IB by VBE. Now we are going to reverse that. VBE by IB, that is equal to R pi value, which is equal to VT by IBQ. Okay, here we can represent the IBQ current. We already know IC is equal to beta times of IB. Beta times of IB. Therefore, IB is equal to what? IC by beta. Okay, here the base current is a Q point current. Therefore, IBQ, and here IC is also becomes the Q point current. Therefore, ICQ by beta we will get. Therefore, VT by ICQ divided by beta, which becomes as beta VT by ICQ. Okay. Therefore, this resistance R pi, which is called as the diffusion resistance, or base to emitter input resistance. Okay. Base to emitter input resistance. The value of this R pi is beta into VT by ICQ. That is a very important equation. This is the component that is present at the input side of our transistor. Therefore, while drawing the equivalent circuit of the BJT, we can represent this R pi, which is a diffusion resistance or base to emitter resistance at the input side of the equivalent circuit. Now we need to get output equivalent component. Therefore, for output collector to emitter port, assuming the collector current is independent of the VCE. Okay, we are assuming that the IC is independent of the VCE, so definitely the IC will be depends upon the VBE voltage. Okay, therefore we can say that delta IC, the change in the collector current, is equal to dou IC by dou VBE at Q point into delta VBE, the change in the base to emitter voltage. We know that I is equal to V by R. Here V is the voltage and 1 by R is nothing but conductance. Okay, we can represent like 1 by R into V, where 1 by R is a conductance. This is the conductance between the output current to input voltage, therefore which can be called as transconductance. This IC can also be written in terms of the time varying component. IC is equal to dou IC by dou VBE at Q point into the VBE, where VBE is the AC base to emitter voltage, that is the time varying base to emitter voltage. Okay, therefore we know that the IC current is equal to Is into exponential of VBE by VT. This is the expression we have seen in the last class. IC is equal to Is into exponential of VBE by VT. Now we are going to substitute this IC value in the above equation. Okay, therefore dou IC by dou VBE, in the place of IC we are going to substitute this equation. Okay, after doing differentiation with respect to the VBE, we can get it like 1 by VT into Is into exponential of VBE by VT at Q point. Okay, here dou VBE by dou VBE will get cancelled. Here when we apply the Q point parameters, this VBE will becomes as a DC component. So this entire term Is into exponential of VBE by VT will be equal to the pure DC current, that is nothing but the DC quiescent collector current ICQ. Therefore, the output conductance GM, which is the ratio of output current to input voltage VBE, that is equal to ICQ divided by VT. Okay, therefore GM is equal to ICQ divided by VT. That is a very important equation. GM is equal to ICQ divided by VT, where GM is called as a transconductance. In the IC current equation, we calculated the conductance value dou IC by dou VBE at Q point, okay, which is equal to GM. Therefore, the IC current equation is equal to this GM into VBE. Okay, then we can write the small signal collector current as IC is equal to GM into VBE. Therefore, at the output side, we have a dependent current source that the value of the source is GM into VBE, and at the input side we got one resistance that is called the base to emitter resistance or diffusion resistance, which is equal to R pi. These are all the two components that are present in the equivalent circuit of the BJT. Okay, then we can represent the small signal hybrid pi equivalent circuit like here we are assuming it is a CE configuration. Therefore, emitter is a common terminal, okay, which was marked here, and the base terminal is the input terminal and the collector terminal is the output terminal. First of all, we have to draw the common line like this. Okay, after drawing the common line, we have to mention the input resistance or base to emitter resistance between the base to the emitter terminal, that is R pi. At the output side, from the collector terminal to emitter terminal, we have a dependent current source that is equal to the GM into VBE. Here at emitter node, this base current IB and the collector current IC, which are getting added, okay, and then which will becomes as a emitter current IE, where emitter current IE is a combination of the base current IB plus the IC currents. Here all values are represented in terms of the time varying components as well as the phasor values. Okay, this is simplified small signal hybrid pi equivalent circuit of a BJT. Okay, so from now onwards in our analysis, wherever we have the BJT, that can be replaced with this equivalent circuit. Okay, then we can apply the KVL or KCL according to our analysis by using this simplified circuit. Next, we are going to get the alternative form of the equivalent circuit. We know that IC is equal to dou IC by dou IB at Q point into delta times of IB. Okay, so here IC by IB is nothing but output current to input current, that is a current gain beta of the transistor. Therefore, change in IC is equal to beta into the change in the base current IB. Like that we can write. Okay, here dou IC by dou beta is called as beta, and where beta is called as incremental or AC common emitter current gain. Therefore, we can write the IC current is equal to beta times of IB current. That is also one of the important equation in our derivations. Okay, collector current IC is the multiplication of beta into the base current IB. Therefore, in the place of GM-VBE, which is nothing but IC current, okay, GM-VBE is nothing but IC current. At that place, we can also represent the beta times of IB. Therefore, the equivalent circuit will becomes like, in the place of GM-VBE, we can get beta into IB. So here, one thing we have to observe, the voltage across R pi resistance is nothing but the base to emitter voltage VBE, which may also called as V pi also. Okay, that is the voltage across the R pi resistance. When we multiply the value of R pi input resistance with the transconductance, we can get, we already derived the R pi input resistance is equal to beta VT by ICQ, and the transconductance value ICQ divided by VT. So here VT will get cancelled and ICQ will get cancelled. We can get it as a beta. Okay, so where beta is equal to GM into R pi. That is also one of the important equation. So next we are going to get the small signal voltage gain of the CE configuration. So here In the place of transistor, we have replaced the small signal equivalent circuit, okay, in this box. Okay, at the input side we have R pi resistance, at the output side we have GMVBE, and the voltage across R pi is nothing but a V pi or VBE, and Vs is the input AC signal source and VCE is the output voltage, which is also equal to the V0. Here the GMVBE current can also be represented like GMV pi. The small signal voltage gain can be calculated as the ratio of output voltage to the input voltage, V0 divided by Vs, like that. So here what is V0? The V0 is the voltage across the RC resistor, and the current flowing in the RC resistor we can take it as IL current. Okay, therefore V0 will be equal to the current flowing in the RC resistor is IL, load current, into the resistance value RC. But IL is nothing but IC current here. Okay, IL can also be represented as IC current, but IL direction and IC direction are opposite to each other. Therefore, minus IC into RC we can write. So, what is IC current? IC is nothing but the GMVBE current. Okay, therefore, IC can be replaced as GMVBE and RC. Okay, that is the value of V0. Okay, here GMVBE can also be written as GMV pi into RC, like that. Okay, so and V pi is equal to, so what is V pi here? The V pi is a voltage across the resistance R pi. Okay, when we apply the voltage division rule in this loop, we need to get the voltage across the resistance R pi. Okay, so divided by the total resistance in this loop, R pi plus RB resistance. Okay, that is the value of the V pi. Okay, so from this equation we can write the Vs is equal to what? Vs is equal to V pi, okay, divided by this entire equation, R pi divided by R pi plus RB. That is the value of Vs. Now we can get the ratio of output voltage to input voltage. Here output voltage is minus Gm V pi RC, and the input voltage Vs is equal to V pi by R pi divided by R pi plus RP. Okay, when we substitute these two values in the AV equation, we can get AV is equal to what? Output voltage minus Gm V pi into RC divided by, here the input voltage is nothing but V pi divided by R pi divided by R pi plus RB. Okay, so here V pi will get cancelled, therefore which will be equal to minus GMRC into this entire term will go to the numerator section, therefore R pi divided by R pi plus RB we can get, that is the value of the small signal voltage gain. Next we are going to see the hybrid-Πequivalent circuit including the Early effect. Here Early is the name of the scientist. He told that the output characteristics of a BJT are linear from the point A. Okay, from the point A, the output characteristics of a BJT are linear. Okay, so actually we treat it as a non-linear, but he said that it is linear from the point A. The voltage at the point is called as a VA, that is called as early voltage. We have assumed that the collector current is independent of the VCE, the collector to emitter voltage. From the analysis of early effect, okay, what we have seen, the early effect, we can write the IC current in terms of IS into exponential of VBE by VT. This is the actual equation. This will get multiplied by 1 plus VCE by VA. Okay, this is the output collector current including the early effect. Okay, which will get multiplied by 1 plus VCE by VA, where VA is called as the early voltage and it is a positive quantity. Output resistance R0 can be given as, here if you see, this is the graph drawn between the output voltage to the output current. Okay, from this graph, the slope of these curves are nothing but the conductance 1 by R naught. Okay, so 1 by R naught is the output conductance, and also R naught is the output resistance, that can be given as the ratio of the output voltage to the output current. R naught is equal to output voltage VCE by output current IC. Okay, so which can be represented as dou VCE by dou IC at Q point. Now we can rearrange this equation like 1 by R naught is equal to the reverse of this one, dou IC by dou VCE at Q point. Here we can substitute the IC collector current equation from this one. Okay, if you treat it as equation number 1, we are going to substitute the value from the equation number 1 here, dou by dou VCE of Is into exponential of VBE by VT into 1 plus VCE by VA at Q point. Okay, when we differentiate this equation with respect to the VCE, here these terms Is into exponential of VB by VT is constant, which can be taken outside. Okay, and then the differentiation of 1 is 0, and here 1 by VA is also a constant which can be taken outside, and dou VCE by dou VCE which will becomes 1. Therefore, the resultant of this differentiation is 1 by VA. Okay, so 1 by R naught is equal to Is into exponential of VB by VT into 1 by VA at Q point. When we apply the Q point parameters, this VBE will become the DC component, and this total term will become as ICQ current, the quiescent collector current. Okay, therefore 1 by R naught is equal to ICQ divided by VA. From the above equation, we can say R naught is equal to VA by ICQ current, where VA is the early voltage divided by ICQ current. Okay, where R naught is called as small signal transistor output resistance. Therefore, at the output side of the transistor equivalent circuit, we may have one more component, that is the output resistance, that is nothing but small r naught. Therefore, hybrid pi-equivalent circuit including the early effect will contains one more extra component, that is R naught. Okay, so in the equivalent circuit of the BJT, we will have the three components here. Now R pi, GMV pi source as well as R naught. These are all the three components that what we have, and alternative method, instead of GMV pi we can write beta times of IB, and these two are the similar one. Okay, the figure 1 is called as transconductance equivalent circuit because it contains the GM term, and the second circuit is called as a current gain parameter equivalent circuit because it contains the beta term. In our examinations, if they have given the values in terms of the current gain, we can use the B equivalent circuit. If they have given the values in terms of the transconductance, we will use the A circuit. Okay, this is about the hybrid pi equivalent circuit of the transistor. Okay, now we are going to see about the expanded hybrid pi equivalent circuit. So in the expanded hybrid pi equivalent circuit, we will have the two extra components. Those are RB, which is the resistance in series with the semiconductor material between the external base to the base terminal B, which is idealized as the internal base B dash. Okay, there is an extra resistance that is connected between the external base to the internal base B dash, and typically the RB value is a very small value, usually smaller. Okay, therefore we can neglect that value. So here if you see, B is called as the external base and this B dash is called as the internal base. Between the external base to internal base, we have a resistance small RB that is called as series resistance or the virtual base resistance. This value of RB is small and we can also neglect that. And one more extra component in the circuit is R mu. Okay, here R mu is a parameter which is called as a reverse bias or diffusion resistance, and the value of R mu is in the terms of the mega ohms. Okay, so which means that a very large value which can be replaced with the open circuit. Okay, therefore we can also neglect the value of R mu. This is the equivalent circuit of the expanded hybrid pi parameters. This circuit will be useful for very high frequency analysis. I hope you understood. In the next class, we are going to see about the RE model and H parameter model equivalent circuit of the BJT.